Aerodynamic damping was first discussed when you were studying drag. We will now see how it can affect static stability. While the pilot is pitching the aircraft, the change in tailplane angle of attack is greater than the change in angle of attack of the wing because the tailplane is moving down. As soon as the pitch angle stops changing, the tailplane and the wing have effectively the same angle of attack. For the study of maneuver stability, we need to consider the period during the change in angle of attack. Study the vector diagram. It shows the tailplane with the true airspeed vector and the speed of tailplane down travel vector. The effective airflow direction is the resultant of the aircraft true airspeed and the speed of tailplane down travel while pitching. You can now see the increase in angle of attack while pitching, which generates an upforce that we know is aerodynamic damping. Aerodynamic damping gives a change in tail force, in this case upwards, while the pilot is pitching the aircraft nose up. At higher altitude, at the same indicated airspeed, the true airspeed is faster, which reduces the change in tail force for the same rate of aircraft pitch change. Let's consider the diagram we used earlier to define the neutral point. The neutral point is the position at which the CG would need to be for the destabilizing wing moment and the stabilizing tailplane moment to be the same. If we now add the change in tail lift to the change in tailplane lift due to a gust, the CG would have to be further aft for the wing moment and the tailplane moment to balance. This CG position is called the maneuver point. The maneuver point will always be aft of the neutral point. If we now look again at the aft CG limit and a sample aircraft CG position, you can see that the aircraft will always have more maneuver stability than static stability. This is because the distance from the maneuver point to the aircraft CG is greater than the distance from the neutral point to the CG. We can now take what we have learned about maneuver stability and apply it to a study of stick force versus load factor. An aircraft with positive maneuver stability should give a steady increase in stick force with increase in load factor, or G. The stick force per G must be positive, but neither too high nor too low. If the stick force per G is too high, the aircraft will be difficult and tiring to fly. If the stick force per G is too low, the aircraft may be accidentally overstressed because of the light control forces. You may be asked to calculate stick force per G, so you need to remember that in level flight the aircraft is at 1 G, and a maneuver that gives a load factor of 2.5 is only a 1.5 G increase. The graph shows a typical stick force gradient. A load factor of 1.6 G requires a 10-pound pull force, and a load factor of 2 G requires a stick force of 18 pounds. These stick force values don't represent any particular aeroplane and are just sample values. Let's now consider the effect of various CG positions on the stick force gradient, starting with the CG at 30% MAC. With the CG further aft at 40% MAC, the stick force gradient is reduced, in that, for the same load factor, the stick force is reduced. With the CG forward at 10% MAC, the stick force gradient is increased. For the same load factor, the stick force is higher. We can now consider the effect of altitude on stick force per G. At higher altitude, the stick force gradient is reduced. This is due to reduced aerodynamic damping. In conclusion, the possibility exists that the forward CG limit could be set to prevent an excessive stick force gradient, and thereby an inability for the pilot to maneuver the aircraft adequately. As the CG moves aft, the stick force gradient decreases, and the lower limit of stick force gradient may be reached, and the pilot could be in danger of too readily being able to accidentally overstress the aircraft. Designers can modify the stick forces if required to give adequate maneuverability throughout the entire flight envelope. The first device that can be used to tailor the control forces is the downspring. The downspring is used to increase the airspeed stick force stability. The downspring consists of a preloaded spring attached to the control system that tends to rotate the elevator down. The effect is to contribute an increment of pull force independent of control deflection or airspeed. The second device used to tailor the control forces is the bob weight. The bob weight consists of an eccentric mass attached to the pitch control system. The bob weight mass is subjected to the same change in load factor as the aeroplane. Thus, the bob weight will provide an increment of stick force in direct proportion to the load factor applied. This will prevent the pilot applying too much G during manoeuvres. The more the pilot pulls back, the more resistance the bob weight adds to the control system. An aeroplane must have adequate controllability as well as adequate stability. As previously mentioned, an aeroplane with high longitudinal static stability will have great resistance to displacement from equilibrium. There are three conditions of flight that provide the critical requirements of longitudinal control power: manoeuvring, takeoff, and landing. Any one or a combination of these conditions can determine the position of the forward CG limit. We will look first at the manoeuvring control requirements. The aeroplane should have sufficient pitch control power to achieve the maximum usable lift coefficient during manoeuvres. The illustration shows that with the CG forward at 10% MAC, the maximum elevator deflection is not capable of trimming the aeroplane at CL max. But with the CG slightly further aft at 18% MAC, maximum elevator deflection is now capable of trimming the aeroplane at CL max. Now for a look at the takeoff control requirements. At takeoff, the aeroplane must have enough elevator control power to be rotated to the takeoff attitude. Anything that increases the nose-down pitching moment will increase the amount of elevator deflection required for the same pitch attitude. For example, if the CG is further forward, or the rolling resistance is increased by, for instance, runway contamination. Now we can look at landing control requirements. When flaring to land, enough elevator control power must be available to rotate the aircraft to the required nose-up attitude. Anything that increases the nose-down pitching moment will increase the amount of elevator deflection required for the same pitch attitude, such as idle thrust, full flap, forward CG, and the aircraft in ground effect. Each of the longitudinal control power requirements are critical for high longitudinal static stability. If the forward CG limit were accidentally exceeded, the aeroplane may encounter insufficient controllability in any of these conditions. To conclude our study of longitudinal static stability, it must be remembered that the forward CG limit is set by the minimum permissible controllability, and the aft CG limit is set by the minimum permissible stability. You must keep your aircraft CG within the forward and aft limits at all times during the flight.